On the first day of this unit, we talked just real briefly about the Dalton model of the atom, otherwise known as the solid sphere model of the atom. The atom is like a billiard ball or like a marble. They can be different, but there's nothing inside these atoms that differentiates them. Okay, that's the solid sphere model of the atom. Thomson comes along in 1897, discovers the electron using the cathode ray tube, and derives from that. He called it the plum pudding model of the atom, but we often call it the raisin bun model of the atom because raisin buns are a lot more familiar to us. The raisin bun model of the atom, where the atom consists of a sea of positive charge. That's the bun. Floating around inside the sea of positive charge is a bunch of little electrons. That's the electron that Thomson discovered using the cathode ray tube. Right? These cathode rays that people have observed for 50 years prior to Thomson, he tells us that they're subatomic negatively charged particles called electrons. Okay, that's the things that are floating around inside this sea of positive charge. Now, this is revolutionary because prior to that, the atom was just the atom. There was nothing smaller than the atom itself. Now, it's revolutionary, but as most of you probably know, this looks nothing like the model of the atom that we currently have. What I'm about to show you is the next logical step in the development of our current model of the atom, which is not what we accept today, but it looks an awful lot like the model of the atom that we have today. We call it the Rutherford model of the atom, or the Planetary model of the atom. Rutherford and his assistants, Geiger and Marsden, used an experiment called the gold foil experiment, or sometimes we call it the alpha scattering experiment. It looked something like this. These guys had this box of radioactive material. I don't know what the radioactive material was, but whatever it was, it decayed via alpha decay. So it decayed and produced alpha particles. These alpha particles got released from this box, one at a time. They get released at the whole of this box. Listen, it's not like we have this box filled with alpha particles and then we're releasing them. We've got this box filled with radioactive material that decays into alpha particles, and then these alpha particles end up getting released more or less one at a time. They get fired towards this really, really thin layer of gold foil. Like we're talking extremely thin, thinner than tin foil or aluminum foil that you use in your kitchen. It would be more like, I don't know if you've ever seen this before, gold leaf that you use on baking for decoration on fancy cupcakes or cookies or something like that. Gold leaf that you can buy in the grocery store that's actual gold, but incredibly thin gold. And you can eat it, yes, you can. It's incredibly thin gold. So this is kind of what we're talking about, something like that, really, really thin like that. It's surrounded by this screen. We call it a scintillation screen. All you need to know is that it's a screen that glows when struck by these alpha particles. So we know where the alpha particles hit based on where this screen glows. So these guys, Rutherford and his assistants, Geiger and Marsden, fire these alpha particles, or allow these alpha particles to be fired one at a time at this gold foil, and they make 3 observations. And from those 3 observations, they make 3 conclusions. The first observation is that most of these alpha particles end up going straight through. We know that because most of them, as they were released from this box, ended up striking the screen directly in front of where they were released. So most of them ended up going straight through. The vast majority went straight through. And that told Rutherford and his assistants something we'll talk about in a few moments here, but gave us a pretty good indication of a certain conclusion about the structure of the atom. The second observation they made was that some of these alpha particles, and remember, most of them went straight through, but some of them didn't go straight through. Some of them ended up going through, but ended up being deflected. The path changed. So some of them ended up going like this or like this. They go through. We know they went through because of where they struck the screen, but clearly by where they struck the screen, they didn't go straight through. Some of the alpha particles went straight through, but were deflected. Now, a few of the alpha particles, remember, most of them went straight through. Some of them went through, but were deflected. A few of the alpha particles ended up bouncing back. Not very many at all, but few of them did bounce back. These three observations led to three pretty solid conclusions. I'll give you an analogy to help you to understand where these conclusions came from. We get a football field, 110 yards on a football field. We got 110 people, one person stationed at every yard marker. We blindfold all 110 people. It's dark outside. They can't see. Nobody can see anything. But who's ever organizing this, who's ever got 110 people stationed at each yard marker, turns the people so that they're facing directly across the football field. So if Jacob is on the 40-yard line on one side of the football field, he's directly aimed at the 40-yard marker on the other side of the football field. We send those people across the football field running one at a time. So Jacob runs across on the 40-yard line. He can't see. He's just running straight in the direction that whoever it was that's organizing this aimed him. Where does he end up? He ends up on the 40-yard marker on the other side of the football field. In fact, of 110 people going across the football field, let's say 100 of them end up straight across. Most of the alpha particles went straight through. Most of the people on the football field went straight across. What does that tell us about the nature of that football field? If 100 out of 110 people ended up running their hardest and going straight across the football field, what does that tell us about the nature of that football field? It's very flat, probably, sure. Okay, yeah, the markers are proper, sure. Probably bigger than that. Nothing got in their way. 100 people ran straight across, nothing got in 100 people's way, right? So this entire football field, we can't see what's on or what's not on this field, but we know since 100 people made it straight across, most of the football field must be clear. Most of the football field must be empty space. The fact that most of these alpha particles went straight through, we know that most of the atom is empty space. Just like most of the football field is empty space. But remember, some of these alpha particles didn't go straight through. Some of these alpha particles were deflected. Let's say of 110 people, 100 went straight across the football field, 8 didn't. 8 made it across the football field, but not on the yard line or the yard marker where they started. So Parker's on the 53-yard line. He's running across. He ends up on the 47-yard line. He was running straight, right towards the 53 on the other side, but something pushed him away from his straight line path. Okay, so here's Parker running across on the 53-yard line, and then he gets somewhere close to it, and then all of a sudden he changes direction and ends up running over there, ends up on the 47-yard line. Parker, remember, is a positively charged alpha particle. What could push a positively charged alpha particle out of its path? What could push a positively charged Parker out of his path? Okay, wind, he says. Okay, if it's Parker, it could be wind, sure. No, a negative charge isn't going to push a positive out of the way. Another positive is going to push a positive out of the way. So Parker's running across, he's positive, right? Positive pushes him away from his straight line path. He ends up over there. So what does that tell us? Oh, there had to be something positive in the middle of that football field. But it's got to be small. Why do we know it has to be small? Because most of the football field is empty space. So whatever isn't empty has to be small. We have a small positive nucleus, we'll call it. We haven't established the existence of protons or neutrons yet, but we have established that there's a nucleus, and it's small, and it's positive. But a few of them bounce back. Well, that could be explained by the nucleus, right? If Parker hits that nucleus straight on, what happens to Parker? Bounces straight back? Depends. Depends, actually. Depends on the nature of that nucleus. If got a water bottle, an empty water bottle here. Okay, got an eraser. Let's say the nucleus is represented by the water bottle, and the alpha particle is represented by the eraser. Okay, so I'm firing the alpha particle right at the nucleus. Watch what happens to the alpha particle. Okay, watch what happens to the alpha particle. The nucleus was knocked out of the way, and the alpha particle just kept going. Now, where did my alpha particle go? Here we are. Let's change the nucleus. Now we've got a water ball that's full. Okay, and watch what happens now when we fire the alpha particle at the nucleus. The alpha particle bounced back, and the nucleus stayed where it was. What was the difference? The mass. Yeah, the nucleus in the second case where the alpha particle bounced back, the nucleus was heavier or denser, right? In order to have these alpha particles bounce back, then this small positive nucleus is heavy or dense. Because if you've got a light nucleus, then the alpha particle is just going to go straight through it, just knock it out of the way. It'd be like Parker running across the football field, running into a 3-year-old, just knocks a 3-year-old out of the way, keeps on going, right? Versus Parker running across the football field and running into a 250-pound linebacker or something, right? He probably bounces back from that guy. So what model of the atom comes from this? It's not our current model, but it's getting closer. Most of the atom is empty space, but there is a small positive nucleus in the middle. Well, we know there's electrons because Thomson discovered electrons in 1897. Those electrons, Rutherford said, just orbit around that small, dense positive nucleus. We call this the planetary model of the atom because it reminds us a lot of the solar system where the planets orbit around the sun. Well, in this case, the electrons orbit around this small, dense, positive nucleus. There's some refinements, some pretty important refinements that we've made to this Rutherford model of the atom that distinguish it from what we currently accept. But this is the first one that looks much like the current model of the atom. When you see a picture of the atom, you usually see it as this nucleus with these electrons just circling around it, orbiting around it. So Rutherford, his assistants, come up with this planetary model of the atom. Sounds good. Niels Bohr comes along. You remember that name as well if you've taken chemistry, Bohr, the Bohr model of the atom. Niels Bohr comes along and says, you know what, this Rutherford model sounds pretty good, actually. This idea that most of the atom is empty space, Bohr said, yeah, I can live with that. Most of the atom is empty space, that works. The nucleus that's in the middle of this atom is small. Yeah, okay, that works, Bohr says. It's dense, it's heavy, sure, that works. Positive, sure. The electrons orbit around the nucleus, sure, that works. So what makes the Bohr model of the atom different from the planetary model of the atom? Seems like everything Rutherford said, Bohr accepts. Well, Bohr said, unlike Rutherford, these electrons that orbit around the nucleus, they can't just orbit wherever they want. Rather, they have to orbit on very specific levels. And if you're going to come up with one word that differentiates the planetary model of the atom, the Rutherford model of the atom, from the Bohr model of the atom, it's levels, the word level. We talk about different aspects of that, but the word level, electron level, is what really differentiates the Bohr model from the planetary model. Each electron orbits around the nucleus on specific levels. Just like when you go to a hockey game at the Saddledome, you can't watch from wherever you want. There's 3 levels of seating. You have to watch from level 1, or level 2, or level 3. You can't be in between levels. You have to be on one level or another. As electrons are orbiting around the nucleus, like when you're orbiting around the rink, you have to be on one level or another. You can't just be wherever you want. Each level is characterized by a certain amount of energy. So level 1 has this much energy, electrons on this level have this much energy, electrons on level 2 have this much energy, and so on. And if you've taken chemistry, we don't really have to know this so much in physics, but if you've taken chemistry, you'll know that electrons always want to fill in those lower levels first, right? Remember that, chemistry people? Like if you go to the Saturday to watch a Flames game, and you're sitting on the third level, you paid your $40 to sit in the third level, and you see 2 empty seats in row 12 in the first level, what do you sometimes do? You sometimes move down, right, to fill in those lower levels first. That's what the electrons do as well. They go down to fill in those lower levels first. Now, there's 3 aspects here. They all relate to electron levels. The second talks about what should happen as electrons orbit around on these levels. Okay, here's my keys here as they're swinging around my head here on the end of my lanyard here. My keys represent an electron. My hand that's holding the lanyard represents a nucleus. As these electrons orbit around the nucleus, they're not speeding up or slowing down, but they're changing direction. They're going in a circle, right? Which means they experience a centripetal acceleration. Remember Maxwell from last unit? What did he say? Maxwell said, accelerating charges generate EMR. Usually we think of charges that are speeding up or slowing down, but it doesn't have to be. As long as they're accelerating, and as they're going in a circle, they are accelerating, they should generate EMR. But they don't here. They don't generate EMR. We know that because if they did, watch what would happen to them. These keys going around my hand, they give off energy. What happens to them as they give off energy? They slow down and spiral in to the nucleus, right? Well, if that happened, how do chemical reactions take place? It's interactions of electrons, right? If you don't have these electrons orbiting around in the way that they do, you wouldn't have chemical reactions. So matter, the universe as we know it, wouldn't exist. It's as if these electrons aren't accelerating. They are, but it's as if they're not. It's as if they're not moving. It's as if they're in a stationary state. Okay, we call it a stationary state, this idea that they're accelerating but not producing EMR. And finally, the third one, we talk about electron transitions. Electrons can make transitions to higher levels. They do that by absorbing energy. How many people have ever sat in the press level of the Saturn on the third level? Yeah? When you go there, you know that when you go there, it's like, it's really high, right? You got to do a lot of stair climbing, right? You better have made sure you had a good lunch before you go there. Absorb some energy in order to climb way up there to the third deck of the Saturn. The electrons can jump to a higher level. When they do that, they have to absorb energy to jump to the higher level. Usually that energy is EMR, not always, but usually. But electrons can also fall to a lower level to fill in those vacancies. You're on the third level, and you see those 2 seats down in row 2 right by the glass. You go down to fill in those 2 vacancies in the lower level. As you do that, you give off energy. You emit energy. And in that case, it would be a photon of some type of EMR or another. You emit EMR. So the Bohr model is different from the Rutherford planetary model in that we have levels. Okay? Each level is characterized by a certain energy. Each level is called the stationary state because the electrons don't emit EMR. And each level of the electrons can change by either absorbing or emitting EMR. So now we got 4 models, right? Dalton solid sphere. We got Thomson Rosenbaum model. We get the Rutherford planetary model, and then we have the Bohr model. And if we had to summarize the Bohr model by one word, it would probably be levels. Yeah, levels. Now, we're going to go through one final slide here. Just going to wrap it up for the day. It's going to just provide us with a little bit more detail about this Bohr model and some of the implications of the Bohr model of the atom here. We got three diagrams here. I'm going to draw a line that separates the first diagram from the second and the third diagram. The first diagram, we're just going to make a reference diagram. We're going to use it for comparison. It has nothing to do with electron transitions per se, but we're just going to use it to compare diagrams 2 and 3, which do have to do with electron transitions. Diagram number 1, you see you have a solid, like a light bulb, the filament of a light bulb that's hot, or you have a liquid that's hot, or you have a gas under a high pressure that's hot. You don't need to know the details of this, but it results in a phenomenon called black body radiation. It generates EMR of every frequency. It generates a rainbow of visible light and a rainbow of non-visible light as well. What does that light look like when it comes off of the solid or the hot liquid or the hot gas under high pressure? It looks like white light. In fact, it is white light. It's all the colors of the rainbow. But that white light, when it goes through a prism, a diffraction grating, or a prism, doesn't really matter which, it splits it up into the rainbow. The only difference here would be the rainbow from a prism would be Roy G. Biv, and the rainbow from a diffraction grating would be opposite to that, right? Viv G, your. So this is what we get on a screen, this rainbow, this continuous spectrum. It's like in my dining room at home, we have this thing hanging from the window in the south-facing backyard, and when the sun comes around to the south in the afternoon, a lot of times on the table, we see this rainbow on the table, this spectrum on the table, right? Basically what's happening is the light from the sun, the white light, all the colors of the rainbow are splitting up into the colors so that we can see them. The table is acting as our screen. That's what we have in our reference diagram here. Nothing to do with electron transitions. It's just this phenomenon of black body radiation. Okay, now let's go to diagram 2. Diagram 2, the only thing we're changing here is that we've got could have had a gas in diagram 1, but it would have been under high pressure. Here we have a hot gas under low pressure. Sometimes they'll say a hot gas under low density gas. Low pressure, low density, whatever. It generates EMR as well, but it's as a result of electron transitions. So an electron makes a transition from high level to a low level, gives off a certain frequency of EMR. Another electron makes another transition, gives off another frequency of EMR, and so on. We don't get a continuous spectrum here because we don't have all the colors of light. We don't have all the frequencies. When we shine that EMR that was generated by this hot gas as a result of electron transitions, so high levels to low levels, through the prism or diffraction grating, it splits it up. But it splits it up into red that was caused by one transition, and orange that was caused by another transition, and green that was caused by another one, and so on. Each of these colors of EMR produced by a different transition. So what do we see here? We call it an emission spectrum. Sometimes we call it a line spectrum or a line emission spectrum. It's a dark screen, except that there's bright lines that correspond to each transition. So instead of having the rainbow, we have just a bunch of lines, each line being a transition. Finally, the last one, if I get rid of this cold gas, that's not working. Let's just do this. If I get rid of this cold gas and pretend the cold gas isn't there, that third diagram looks an awful lot like the first diagram, right? In fact, it should be exactly the same. What's different? I get rid of the cold gas. What's different about the third diagram from the first diagram? The lines. So it must be this cold gas that resulted in these lines, right? It's the only thing that makes it different. What's happening here? Well, remember, you've got this hot solid or this hot liquid or this hot gas under high pressure. it generates white light. True white light. It generates all the colors of the rainbow. It just appears white. It goes through the cold gas. If it didn't go through the cold gas, it would go through the prism or diffraction grating and produce a continuous spectrum. But when it goes through the cold gas, what does it do? It takes away some of the white light. It absorbs certain photons, causing electrons to jump to higher levels. So now what you see over here is, well, what you saw up here, the continuous spectrum, minus a red light photon. Why is that gone? Because it was absorbed by the cold gas to cause the electrons to jump to a higher level. And it's minus an orange and a couple of greens and some blues and indigos and violets. Each one corresponding to a transition from a low to a high level when the cold gas absorbed a photon. That makes sense? Besides the fact that one is dark lines and one is bright lines, what do you notice about diagram number 2 and diagram number 3? The hot gas versus the cold gas. What can you tell me about this hot gas as compared to this cold gas? This hot gas is emitting certain frequencies of EMR. This cold gas is absorbing the same frequencies, right? What does that tell you about this hot gas versus this cold gas? It's the same gas. This is like a fingerprint. Each gas, each element, each compound has its own unique fingerprint or its own unique spectrum. That means that if we observe a spectrum, we can compare it to some other known spectrum and determine what it is. If you discover a star and you shine the light from a star through a spectroscope, prism or diffraction grating, and you observe the line emission spectrum that's produced, you can compare it against known spectra and determine what it's made out of. Determine the composition of that star, not by visiting the star, but just by looking at the transitions of electrons that are taking place. It's like, the police officer can determine that you were at a crime scene because your fingerprints, the fingerprints taken at the crime scene, match up with known fingerprints. Okay? The fingerprints, the emission spectrum from that star matches up with a known emission spectrum. Let's say in this one we have an unknown gas mixture that was, I don't know, we observed this from some new star that was just discovered. If this was a diploma exam question now, this would be in full color, but whatever, pretend it's in color. We want to determine what makes up this star. We compare it against our known spectra on the left here. How many people think hydrogen would be present in this unknown gas mixture? Who says hydrogen would be present in this unknown gas mixture? Yeah, Benton, why do you say hydrogen is present?
Because a lot of other people think.
Okay, you know what? That's usually a good way to go. When a lot of people say that this is the answer, usually it is, unless they're all trying to trick you. It's a big conspiracy. That might happen. Somebody else with maybe a different answer on that? Yeah, the lines match up, right? Not all of them, but all of the lines from hydrogen, like all of the lines from hydrogen are present in the unknown gas. So hydrogen must be there, right? What about helium? Are all the lines from helium in the unknown gas? Nope. There's some that aren't there, so therefore helium isn't present there. What about sodium? There's 2 lines in sodium. Are they both present in the unknown gas? Sure enough, they are. So what do we know about the composition of the unknown gas? It's hydrogen and sodium. So this light's coming off of this newly discovered star, goes through a spectrometer. You compare it against known spectra, and you decide, oh, must be hydrogen and sodium makes up this star.